Hi, I'm Stephen Neshiba, and I'm here to help you out with helping you identify some unknowns in a gas lab based on densities of the unknown gas. So I'm just going to take you through a few equations and some bit of strategy here. So here's some key equations. First one is that the number of moles of any substance is equal to its mass divided by its molar mass. That's true of anything, but now if we're dealing with an ideal gas, you probably also know that that's the number of moles is equal to pressure times volume divided by R times T. So those are some pretty good, important theoretical equations. There's also equations having to do with the density of a gas, and so I've indicated the density by this Greek symbol rho, and that's equal to the mass of a sample divided by whatever volume the sample is taking up. And if you have an ideal gas, then that would be equal to the molar mass times the pressure, which you would measure, presumably, divided by R times the temperature in Kelvin. So, for example, the gas constant in this case will be 0.082 liter atmospheres per mole Kelvin. That would be useful, for example, if you were trying to calculate the density of air, which I've kind of taken you through here. Air has a molar mass, that symbol there, about 29 grams per mole. Let's suppose you measure the pressure to be 1.01 atmospheres. There's R, and there's the temperature in Kelvin. And you'll want to take this through more carefully and also make sure you measure the actual pressure and the actual temperature. But, the number that we're looking at is probably around 1.2 grams per liter. And, you might want to do that for several other gases. All the other possible gases in the list of possible unknown gases would be another set of numbers like that. Now, so that's the theoretical part. So how are you going to use that? Well, here's a possibility. One, let's suppose we've got an Erlenmeyer flask there. It's got a certain amount of volume of the airspace in it. Got a stopper on it so that the gas doesn't get out. If you were to weigh this on an analytical balance, let's say that would be M1, okay, and let's see, that would be the mass of the flask with no air or gas at all in it, plus whatever the mass of the air was. If you had a different gas in there, say the unknown gas, then this term would change. So let's suppose you weighed both of those to 4 or 5 significant figures, which we can do on our analytical balances. Well, then, how about this? You could take the difference between those two masses that you measured, the mass with the unknown gas in it, the mass of the flask, and then the mass of the flask with air in it. Okay, well, obviously the mass of the flask would cancel out in those two cases, and then you'd have that number that you measured would be the difference between the mass of the unknown gas in your flask and the mass of when there was air in it. How does that help you? Well, let's just use some of our equations here. The mass of air that's in your flask, well, you could solve this equation here and say, well, I know the volume of the airspace in there, and you would have already calculated the density of air right there. So you can solve that equation. You get the mass of the air inside that flask. So, through that theoretical calculation, you can get the mass of the air. Since you've already measured M1 and M2, then you know that. And so the only unknown left in this equation is the mass of the unknown gas that's in your flask. Okay, that's good. So now you know that. How is that going to help you identify what gas it is? Well, we can go back to our equation here and say, well, if that was the unknown gas mass that was there, and it's still in the same volume, you'd be able to calculate the density of an unknown gas, the unknown gas that you're in here, just by using that equation straight up. And then you could compare it to the densities of all the possible unknown gases, and the one that makes the best match would be your unknown. So that's a strategy. Okay.